Let's go over the warm-up review. First question, what are the branches of the common hepatic artery? So there's the gastroduodenal artery, which gives rise to the right gastroomental artery, which is also called the right gastroepiploic artery. Then the other branch of the gastroduodenal artery is the anterior superior pancreaticoduodenal artery. Then the second branch off the common hepatic is the right gastric artery. And the third branch is the hepatic artery proper, which gives rise to the left hepatic artery and the right hepatic artery. And the last one, which cell type secretes the histamine that stimulates the histamine receptor on parietal cells of the stomach, thereby increasing gastric acid production? This is the enterochromaffin-like cells, or the ECL cells. Now let's move on to the lecture.
Hi, this video is the first of the Medicine in Society portion of the course, which is kind of a grab bag of several very important high-yield topics, including biostatistics, healthcare economics, and medical ethics. Now, in addition to being an infectious disease physician, I also have a Master of Public Health degree. So I'm going to kick off Medicine in Society by discussing some evidence-based medicine topics related to research study designs. The material in this video and the next is incredibly high yield. Students are often upset that they didn't spend more time studying this stuff because it's so high yield. So you really want to pay attention to this video. I think it's going to pay off for you. So let's dive right in and talk about some different ways that you could design a research study. We'll start with case control studies. A case control study compares a group of people with disease to a group without disease to look for potential risk factors or exposures that could account for the bad outcome. So this is the kind of study that the CDC or other public health entity might undertake if there's a disease outbreak. What you do is you take a group of people that all have the disease and put them into one group, and these are called the cases. And then you take a group of people who don't have the disease but are otherwise similar, and these are the controls. Then you look back over all of their recent food intake, environmental exposures, travel histories, etc., to see how these two groups, the cases and the controls, are different. And hopefully this leads to some exposure or risk factor that's linked to the bad outcome. So what I just described is both retrospective and observational. Like I said, as the investigator, I would take a history of exposures for the two groups. So I would ask all of the study participants to look back over some period of time and tell me what their exposures were. That backward-looking element to the study makes it a retrospective study. Besides being retrospective, case control studies are purely observational. There's no intervention here. There's no experimental arm. I was just observing what the cases and controls did in their everyday life. I, as the investigator, didn't intervene in any way. I merely observed what took place. So case control studies are retrospective and observational. It's important to remember that case control studies are used to identify risk factors for diseases, but this does not always mean that the identified risk factors are causal. All we can say is that there's some association between the risk factor and the disease. The outcome of a case control study yields an odds ratio. An odds ratio takes the odds that someone with the disease had the exposure in question and compares it to the odds that someone without the disease or the control also had that exposure in question. For example, you can measure the odds ratio for smoking and lung cancer. Smoking would be the exposure and lung cancer would be the disease. Then you would look at the odds that someone with lung cancer having smoked and divide it by the odds that someone without lung cancer has smoked. And the odds ratio can also be interpreted as the odds of having the disease from someone among the exposed divided by the odds of having the disease from among the unexposed. This is just another way of looking at the odds ratio. We'll talk more about calculating odds ratios later on. Next, let's look at cohort studies. Now, a cohort is a group of people that have something in common, like a common exposure. So you can have a group of people that have all had a certain exposure, say asbestos exposure, and compare them to a cohort of people who had not had asbestos exposure. Then you follow both cohorts to see what the outcomes are among the exposed versus the non-exposed. This is still purely an observational study. We still aren't doing any sort of intervention here. But a cohort study could be either retrospective or prospective. An investigator may form a cohort based on a recent exposure and follow the participants into the future to see what the outcomes are. Alternatively, the investigator may look into the past, form a cohort out of people who all had a certain exposure at some point in time, and then follow them over a set period of time to see if the outcome of interest ever developed. In this case, both the exposure and the outcome all happened in the past. So to summarize, in a case control study, you take a group of people with a bad outcome and then compare them to a group without the bad outcome and look back at all of their exposures to determine risk factors. In a cohort study, you take a group of people with an exposure or risk factor and then see what happens to them over time. So how do we analyze cohort studies? Cohort studies yield a relative risk or a risk ratio. So a case control study gives you an odds ratio, and a cohort study gives you a risk ratio or relative risk. To calculate relative risk, you divide the risk or rate of the disease in the exposed group by the risk or rate of the disease in the unexposed group. It tells you how many times greater the risk for a bad outcome is among the exposed compared to the unexposed. Now, this may sound a lot like odds ratio, and it is. The odds ratio, though, is considered an approximation of the relative risk. In a case control study, the total population can't be known. So a true relative risk can't be calculated, but an odds ratio can. And that odds ratio stands as an approximation of a relative risk. But a cohort study does have the population variable, so you can calculate a true relative risk. Now, let's move on to cross-sectional studies. A cross-sectional study looks at a population at one point in time. Say you want to know how many people in the U.S. have COPD at one point in time, say January 1st, 2016. This study will tell you how many people in the U.S. had a diagnosis of COPD as of January 1st, 2016. You can also ask about risk factors. This will tell you how many people were smokers or were exposed to secondhand smoke on that day. This study will then give you a snapshot picture of the population and COPD at one point in time. So from this study, you can estimate how many people in the U.S. have COPD and how many of them have known risk factors. This is a quick and easy way to figure out how many people in a population have a disease at any point in time, which is known as prevalence. However, there's a lot of things that a cross-sectional study can't tell you. It can't tell you how many people are developing the disease every year, which is known as the incidence. And it can't tell you if the disease is becoming more or less prevalent. It can't tell you how the exposures and the disease outcomes are related over time. So it can't demonstrate causality. So a cross-sectional study is observational. Since we're not manipulating any of the study factors, we're just merely observing what people are doing at a given point in time. And we would not say that it's retrospective or prospective because it's only looking at one point in time. Another type of purely observational study is the twin concordance study. A twin concordance study compares concordance rates of diseases or traits in identical twins and in fraternal twins to measure heritability of those diseases or traits. A similar study is the adoption study. By studying twins that were raised in separate homes, these studies usually seek to determine the impact of genetics versus environmental factors, the old kind of nature versus nurture question. Now let's move on to clinical trials. What's a clinical trial? A clinical trial is an experimental study where the investigator is intervening to draw a conclusion. So we've moved beyond that pure observation to intervention. The investigator is giving one group of participants the experimental therapy and another group of participants either a comparison treatment or a placebo. Now, with the clinical trials, you're using human subjects, and that's a huge deal. Clinical trials are expensive and they can be dangerous. So how do you make them high quality and reliable? One way is to make them controlled, randomized, and double-blinded. What does all that mean? Well, controlled means that there is not only an experimental group who receives the experimental treatment, but there's also a control group that gets either a placebo or a comparator drug that's well known. And in this way, the experimental group can be measured against another group that's receiving a known treatment. Now, randomized refers to the participants being randomly assigned to the experimental group or the control group, and this is to limit bias. Now, double-blinded means that the study design does not allow either the participant or the investigator to know whether that participant is receiving experimental treatment or the control drug or placebo. So that's a little bit about the basic design of clinical trials. Now let's talk about the phases of trials that we use to develop new drugs. I'm going to sum up each of these phases for you in a simple question. The question for phase 1 trials is the drug safe? In phase 1 of a clinical trial, you're giving the drug to healthy volunteers in order to determine if the drug is safe and what the pharmacokinetics of the drug are. So in phase 1, you want to know if the drug is safe in healthy volunteers and how a healthy body handles that drug. So phase 1 determines if the drug is safe by looking for toxicities. Who participates in these phase 1 trials? You probably know. College students. There are a lot of healthy college student volunteers participating in phase 1 trials. Young, healthy individuals. Actually, a lot of times will use medical students, so maybe you've even participated in this phase of a trial before. For phase 2 trials, the question we're asking is, does the drug work? So you look at patients with the disease. This is the stage where they give the drug to a few patients with the disease to measure efficacy of treatment, appropriate dosing, and again, adverse effects. So in this phase, you're giving the drug to the target population to see if it works in the population that it's intended for. Then the question for phase 3 trial is, does the drug work better? Is it better than a placebo or better than the established treatment? So phase 3 trials are the trials that you commonly see in medical journals, where you're comparing an experimental drug to the drug that already exists on the market. The question is, does it work better? Does it work better than what's already out there and is currently recommended? Then phase 4 is post-marketing surveillance. So a drug company has to provide data from their phase 1, 2, and 3 clinical trials in order to get an FDA approval. Then once the drug is approved and it's on the market, they still have to monitor for additional problems. This is when some of those less common adverse effects come to light, once that drug is broadly marketed and widely used. So this phase is good for identifying rare adverse effects or long-term effects of therapy. And you can imagine that it takes a very long time to get through all of these phases of trials, and it's very expensive. Okay, let's briefly talk about one other study design that's important to understand, and that's the meta-analysis. A meta-analysis combines data from many studies in order to provide better insight than any one of those studies would have been able to provide individually. By combining several studies together, the investigators can increase the statistical power and thereby reach statistically significant conclusions that may have been hidden when the studies were evaluated individually. So as an example, say there are a lot of studies looking at statins and the risk reduction for myocardial infarctions. So you take each of these statin studies and combine them all together and see if, as a class, those statin drugs reduce overall risk of an MI. So you're pooling studies together. And there are a lot of pitfalls inherent to meta-analyses. The investigators themselves are responsible for outlining the inclusion criteria for the related studies and are also responsible for judging the studies based on those criteria. And this is where this selection bias creeps in. We'll talk about bias in another video. Also, the quality of the entire meta-analysis depends on the quality of each of those individual studies. So all this to say that meta-analyses have some major strengths. There's also some major potential weaknesses there. All right, that is it for now. Let's go through your end of session quiz. Go ahead and pause the video, answer those questions, and then we'll go through the answers together. All right, let's get started. A physician is looking for risk factors for pancreatitis, and he interviews 100 hospitalized patients with pancreatitis and 100 hospital patients without pancreatitis. What type of study is this? This is a case control study. He's looking for risk factors, and he's starting with a diseased population and then looking for exposures retrospectively. Next, a group of smokers and a group of non-smokers are followed over 20 years, and every 2 years it's determined who develops cancer and who does not. What type of study is this? In this study, you're starting with an exposed population and then looking for a specific outcome. So this is a cohort study. Next, can a cross-sectional study help determine incidence or prevalence of a disease? Remember, a cross-sectional study looks at a population at one point in time. It can tell you about the number of people with disease or risk factors at one point in time, and that's prevalence. But it can't tell you how many people are developing a disease, and it can't determine causality. All right, that's it for our lecture on research study designs. I'll see you next time.